In this lecture, we will look at the adsorption of a gas or a solid, gas or a liquid on a liquid or a solid surface. A great deal of chemistry takes place on solid surfaces, and therefore we must know about adsorption and the rate of absorption and how it depends on both the rate constants and the concentration of the adsorbent in the solution or in the gas phase. Another example where such information is important is the deposition of semiconductors on solid surfaces. Now, there are two types of adsorption. The first is physical adsorption, also called physiosorption. As the name suggests, in this case, the adsorbent, which might be a gas or a liquid molecule, adsorbs on a surface by means of mainly van der Waals interactions. In some cases, it can also be electrostatic interactions. And because the van der Waals interactions are quite weak, the amount of heat or enthalpy released upon adsorption is typically 20 kilojoules per mole or less. Such adsorption is typically not very important in terms of what we are going to do. The second type of adsorption is called chemiadsorption. Or chemical adsorption. Here the adsorbent covalently links to the adsorbing surface. So you might have an adsorbent A, and this might react with this surface to form something like this. Since this is a covalent reaction, the amount of heat released is almost a order of magnitude higher. It is about 100 to 500 kilojoules per mole. Now, usually heat is released. The reason this occurs is because since adsorption is a spontaneous process, the change in Gibbs free energy must be negative. Now, the adsorbent, which was free in solution or in the gas phase, is now adsorbed on the surface, and therefore there is a large loss of entropy for the adsorbent. This negative loss of entropy must be compensated by a negative change in enthalpy, and therefore these are exothermic reactions. The only cases where this may not occur is when the adsorbent has a high surface entropy, so it can diffuse on the surface. There are very few examples of this. One example is where hydrogen gas gets adsorbed onto glass. We will now look at what are called adsorption isotherms. In adsorption, isotherm relates the amount of substance attached to a surface to its concentration in the gas or the solution phase. To do this, we define something called surface coverage, which we will also call theta, and this is equal to the number of occupied sites on the surface divided by the total number of available sites on the surface. So in all these cases, the free gas or free liquid is in equilibrium with the adsorbed gas or adsorbed liquid. And this equilibrium depends on the partial pressure of the gas or the concentration of the adsorbent in the liquid phase. So the graph of this theta versus pressure or concentration at a given temperature is called an adsorption isotherm. The simplest type of adsorption isotherm, and also the most important for our purposes, is the Langmuir isotherm, which was developed by Irving Langmuir in 1916. Okay, so there are various assumptions involved in the Langmuir isotherm. The first is that all parts of the surface behave uniformly. So there are no defects. Every part of the surface behaves uniformly. The second assumption is that each adsorption site is independent of other adsorbed sites. So if I have this surface, so the adsorption at this site will not influence the adsorption of this site, and so on and so forth. And the third assumption is that the maximum coverage you can have is the maximum available number of sites on this surface. Okay, making these three assumptions, one can make the formalism for the Langmuir isotherm. Here we have a material A, which can be in the gas or liquid phase, and this will adsorb to a surface S to form AS. So the reaction can look like something like this. There are two rate constant. One is the forward rate constant for adsorption, and the other is the backward rate constant for the desorption. Now, adsorption can only occur when a molecule hits the surface, and the number of molecules that hit the surface depend on the concentration. So the rate at which adsorption occurs must be proportional to the concentration of the species which is getting adsorbed. It is also proportional to the number of available sites. So if n is the total number of available sites and theta of them are already occupied, then the number of occupied site is n theta, and the number of unoccupied sites is 1 minus n theta multiplied by n. So the rate of adsorption must also depend on the number of adsorption site. Therefore, the rate of adsorption is equal to the rate constant multiplied by the concentration multiplied by n multiplied by 1 minus theta. The rate of desorption is equal to the rate constant of desorption multiplied by the number of sites which are already occupied, because no desorption can occur from a site which is not occupied. At equilibrium, these two must be constant since there is no additional adsorption or desorption of material. So the adsorption rate constant multiplied by the concentration of the species multiplied by the total number of sites multiplied by the fraction of unoccupied sites is equal to the desorption rate constant multiplied by the total number of sites multiplied by the fraction of occupied sites, not available sites. If we rearrange this equation, we can write the fraction of available sites, adsorbed sites as K multiplied by the concentration of A plus 1 divided by 1 into K multiplied by the concentration of A, where K is some kind of equilibrium constant. It is the ratio between the two rate constants. This is called the Langmuir isotherm. Let us look at what happens when the concentration of A is very small. So at very low concentrations, K multiplied by the concentration of A is much smaller than unity. Therefore, theta becomes equal to K multiplied by the concentration of A. So at low concentration, we are in the linear regime. We can also write this equation in another form. We can write it as 1 minus theta is equal to 1 divided by 1 plus K multiplied by the concentration of the adsorbent. So all you do is subtract this from 1 and you get this equation. At very high concentrations of A, this term becomes dominant and much greater than unity. Therefore, 1 minus theta becomes proportional to 1 divided by the concentration of A. So these are the two extremes. So let us plot how this Langmuir isotherm will look for this simple system. On the x-axis, you have the concentration of A. On the y-axis, you have the fraction of available sites. So the idea here is to predict how much adsorption will occur as I increase the concentration of my adsorbent. And if you plot this equation here, it will look something like this. And of course, the maximum fraction of adsorbed sites will be equal to 1. At low concentration regimes, which is this region, theta is linear with A. You can clearly see that this is almost a straight line. So in this regime, theta, the fraction of available sites, is proportional to the ratio between the rate constant multiplied by the concentration of A. In this region, we have the standard Langmuir isotherm. We don't make any assumptions here, additional assumptions here. And in this region, when the concentrations are very high, then 1 minus theta is approximately equal to 1 divided by K concentration of A. So this is what the Langmuir isotherm looks like for the simple case where an adsorbent adsorbs onto a surface which is uniform and each adsorbing site is independent from the other. We'll do some exercises where we make a plot to verify whether something follows the Langmuir isotherm. To do that, what you can do is you can plot 1 by theta versus 1 by the concentration of A. So the inverses. So if you look at this equation here, what you will get is 1 by theta equals 1 plus K times concentration of A divided by K times concentration of A from this equation. And this is equal to 1 by K times concentration of A plus 1. So if an adsorption process follows the Langmuir isotherm, the plot of 1 by theta versus 1 by A must be a straight line. So it should look something like this. And the slope of this line will be equal to 1 divided by K. And you can extrapolate to very high concentrations of A. All right, we will do 1 or 2 exercises regarding this, and you will also do this in your laboratory. So this was the simplest case. Let us take a slightly more complicated case. And here we have adsorption with dissociation. I can never get this right. Adsorption with dissociation. What does that mean? You have a material such as A2 now, and it adsorbs on a solid surface, but it does so along with dissociation. So one atom adsorbs on one side and the second atom adsorbs on two sides. The most simple example of this is hydrogen atom being adsorbed on glass to form two hydrogen atoms linked to glass. In this case, the adsorption kinetics are bimolecular because now you have two sites where the reaction can occur, and therefore the rate of adsorption is given by the forward rate constant multiplied by concentration multiplied by the square of the fraction of available sites. And the rate of desorption is also bimolecular, and this is equal to kd theta square n squared. And then you can make the same mathematics as below as earlier, and then what you get now is that the adsorbed fraction is equal to the square root of K multiplied by the concentration of A divided by 1 plus the square root of K multiplied by the concentration of the adsorbent. And again, at low concentrations, this factor becomes negligible and the fraction is approximately equal to the square root multiplied by the adsorbent concentration in the bulk phase. And at high concentrations, 1 minus theta is approximately equal to 1 by square root of K multiplied by A. So this is for a case where there is dissociation. Now instead of 2, if there were 3, available sites, then the equation will change accordingly. It will become theta equals K concentration of A, and now to the power of 1 by 3 instead of 1 by 2. And this is also the Langmuir isotherm. So this is the simplest isotherm, but for non-ideal systems, we typically use more empirical isotherms. So you measure the concentration and you measure the rate of adsorption, the amount of adsorption. And one such isotherm is called the Freundlich isotherm, which says that the amount of material adsorbed is equal to a rate constant multiplied by a concentration to the power of n, an exponent n. This n is usually less than equal to 1. And then you can take logarithms on both sides. And measure both n, and K, the rate constant. Now one of the assumptions here is that there is no saturation. You can keep absorbing more and more material, right? So in the previous case, there was a saturation. This equation here, this looks very much like the Michaelis-Menten kinetics of enzymes. But in this case, there is no saturation. As you keep increasing the concentration, more and more material gets adsorbed. Sometimes this equation is written in a different form. The number of moles or the number of occupied sites is equal to some constant Q multiplied by concentration to the power of 1 by m. And in general, m is greater than unity. This is just a different form of this equation. And again, you can take logarithms on both sides. And by plotting log C versus log n, you can calculate both Q and 1 by m. Here also you are plotting log n versus the concentration of A. So these are two types of isotherm which is used for adsorption of simple materials on surfaces. In a later lecture, we can look at Langmuir blodgett films or Langmuir monolayers on liquid air surfaces. So this is liquid and this is vapor. And if you put some material which looks like this, in this phase, this part is hydrophilic, this part is hydrophobic, this could be a surfactant, then the material will partition like this and will form a monolayer. Now you can decrease the area by moving these partitions and look at the phase behavior of the system. But this is for a later lecture.